This is section 2.3, functions and relations. In order to determine whether a relation is a function, we need to talk about what each of these mean. The definition of a relation is quite simple. It's just a set of ordered pairs. And these ordered pairs are usually given with an x and a y component. And the set of all of the x values in those ordered pairs is called the domain of the relation. And the set of all y values in the ordered pairs given is the range of the relation. Now, we do have a very special type of relation, and it's called a function. What makes a relation a function? Because not all relations are functions. Well, in order to say that y is a function of x, we need for every value of x in the domain to only have one y value. So in other words, we cannot have any repeated x values. Because if we had repeated x values, then we would not have unique y values for every x value. So let's go ahead and take a look at this first example. Here we're given a relation, but as you can see, when x is 2, y is 3, and now we have when x is 2, y is 4. So what do we have? We have the same x value. But what do we have? We have different y values. Okay, so we do not have a function. Okay, let's go ahead and look at the relation in number 2. I do not see any repeated x values, so we are good, and yes, we have a function. Looking at number 4, this is a linear. This is the graph of a line. So yes, this is a function. Now, how would you think about that? Because for every x value that you multiply by 2 and add 6, you're always going to get a unique y value. Okay, in number 5, as you can see, this is actually a quadratic, and here, for every x value that you square, multiply 2, add 6, you're only going to get y value, one y value. This will not generate more than one y value for each x value. We're going to learn an easier way other than just looking at these. I did skip over number 3 accidentally, so let's look over there. No repeated x values. So we do have a function. Now, looking here, as you can see in number 6, let's go ahead and rewrite this. So let's add y to both sides. And then, let me write that in a different color. And then let's go ahead and subtract an x. So we will have y is equal to 7 minus x. And here again, we have linear. For every x value, there is a unique y value, and this is yes. Now, as you can see here, if we go ahead and solve this for y squared, so what will we do here? We will subtract 7. Lots of ways to solve these. And then multiply everything by a -1. So we will have negative x plus 7 is y squared. And let's just turn that around. And as you can see, for every x value, we are going to have two different y values that could be possible, up to 2. So this is a definite no. Okay, it is not a function. Now you could continue on. Let me move that no up here. And why is that? So we would have plus or minus the square root of 7 minus x. So as you can see, for the same x value, we would have two y values. So it's not a function. Okay, now looking at number 8, let's go ahead. Let's try a different way this time. Let's add y cubed. So we have x plus y cubed is equal to 7. And then, let me move that. And then we can subtract x. We'll have y cubed equals 7 minus x. So y is equal to the cube root of 7 minus x. So there is only one y value there for every x value. So this is a yes. Now some of these you might be thinking, well, that's going to be difficult. So let's now find a way that if we could graph some of these functions, we might be able to see if we graph some of these relations, we might be able to see if we can tell if it's a function or not. So we will use something called the vertical line test. And there's a very important word in this test. So if a graph defines y as a function of x, no vertical line intersects the graph in more than one point. No vertical line. So that means every vertical line possible can only hit the graph one time at most. Okay? Then it would be a function. So let's see. Let's take a vertical line here. And we hit the graph in two different places. So this is a no. Now here I could draw a vertical line here, 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 and I only hit the graph one time. So this is a yes, anywhere that you would draw a vertical line. Now in number 11, we have to be careful because we only hit the graph once there, once there, once there. But look at this. If we draw a line there, we've actually hit 2 points on the graph. So this is a no. But let me give you a counter example. What if the graph came down and it was closed here and then open here? So what would you notice? If we drew a vertical line through there, and I didn't do a very good job there. If we drew a vertical line here, we would only hit the graph once, once, and once. So this would be a yes, okay? So now let's move on to function notation. And it's very nice notation, and we call this f of x, and that is this. So what we're going to do is we are given a definition of a function here. And this is for every value of x. So now our x this time is -3. So everywhere there is an x, we are going to write a -3. And it's really important to take the time to write that and then to simplify. And if you add all of that together, you will get 28. Let's try that in B. We're going to do the same thing. everywhere, and I might even show you here, everywhere that there is an x, we're going to put that x in those places. So now we are going to have 2 times the square root of 2 squared minus 3 times the square root of 2 plus 1. Well, when we square the square root of 2, it's just 2. And then we end up with 4 minus 3 root 2 plus 1. And now we can combine these two like terms and have 5 minus 3 root t. Okay. Put that up just a little bit. Okay. Taking a look at C, we want everywhere there's an x, we're going to write an a. So this is 2 times a squared minus 3 times a plus 1. And that's it. Looking at D, and I can probably move this down here. And in part D, we have everywhere there's an x, we're going to write 3 plus z. So we have 2 times 3 plus z squared minus 3 times 3 plus z plus 1. Now we have a little algebra to do. So we will be squaring these binomials. So we're going to work on the inside first. And 3 plus z times 3 plus z is, we can write that out maybe over here, 3 plus z times 3 plus z. So we'll do first outer, inner, last. Okay, so first would be 9, outer 3z, inner 3z, and last is z squared. And then let's distribute that negative 3 plus 1. Now we do have like terms here. This is 6z, so when we distribute that 2, we'll have 12z. And then we can combine this. Well, we'll have time to do that next. Minus 9 minus 3z plus 1. So sometimes it's nice to put a little loop under the constants. And then if you see any other like terms, maybe you can write a line or something. So let's go with our z squared first. So we just took care of this term. And now let's add our z's. 12z minus 3z is 9z. And then we have 18 plus 1. And then we have 18 plus 1 minus 9. So that would be a 10. Okay. Well, what if we have this next example where g of x is given as the square root of 6 minus 2x. Let's take a look at that. So here we're going to find g of 3. So everywhere there's an x, we're going to put a 3. So we have the square root of 6 minus 2 times 3, square root of 6 minus 6, and that's 0. And in B, we're going to have the square root of 6 minus 2 times 4, and that's the square root of 6 minus 8, which is the square root of negative 2. And this is not a real number. This is undefined. Okay, square root of a negative number is undefined. See if I can make that just a tad bit smaller. Okay, let's go to G. So here we're going to have G of negative 4. We have the square root of 6 minus 2 times negative 4. That's the square root of 6 plus 8. And we have the square root of 14, which we cannot simplify. Put that there. Okay, and now G of 2w, and that's going to be the square root of 6 minus 2 times 2w, which is the square root of 6 minus 4w. Okay, now we're going to be finding intercepts. And intercepts are really easy because if you want to find the x-intercepts, you're going to let y be 0. And when you look for the y-intercept, you're going to let x be 0. As you can see here, x is 0, and of course f of x is y, so we're letting y be 0. So let's go ahead and find our x-intercepts and our y-intercepts. Let's start with our x-intercept. And here we're going to let y be 0, and we're going to solve that. So now we're going to add 4 to both sides. 4 equals x squared. Let's write that as x equals 4. And then x is equal to plus or minus the square root of 4, so plus or minus 2. So our two x-intercepts are x equal to 2 and x equal to negative 2, and we can create points for those. So we have negative 2, 0 and 2, 0 as the points generated from those intercepts. Now, if we want to find the y-intercept, why don't I switch this down here? The 2 points generated are negative 2, 0 and 2, 0. Now, if we're going to find the y-intercept, we're going to let x be 0. So let's write this down. So we have y equals x squared minus 4. And here we're going to let x be 0. So y equals 0 minus 4. And y equals, negative 4. So what point do we have now generated? We let x be 0 and y is negative 4. So really makes it easy if you can remember those steps. Let's give this next one a try. For our x-intercepts, we're going to let y be 0. And I'm going to add the absolute value of x to both sides. So I'll have the absolute value of x is equal to 3. And so we have x is equal to plus or minus 3. That generates 2 points. We have negative 3, 0 and 3, 0. For the y-intercept, we're going to let x be 0. And y is 3. And so now we have 0, 3 as the point on the graph. Okay, let's give this last one a try. So we have an x-intercept. We're going to let y be 0. So we're going to add root x to both sides. Whoops. And so we'll have the square root of x is equal to 2. And now when we have the square root of x equal to 2, we will square both sides, and we will have x is equal to 4. So now we have 4, 0 as a point on the graph. Finally, our y-intercept here, we're going to let x be 0. So we have y equals 2 minus the square root of 0. And we have y equal to 2. And now we have 0, 2 on the graph. So finding our x and our y-intercepts, these will give us points on the graph quickly. Okay, and now let's talk about our domain and range of a function. And as we stated earlier when we talked about relations, the domain is the set of all x values in the function, and the range is the set of all y values in the function. So we're going to take our time here. As you can see, every x value, you can see these arrows, these will go on and on. So all of the x values are covered on this graph. So our domain is all reals. Now, if you will notice, our range begins here and goes up. Our range are our y values. So our range starts at y equal to 2 and goes all the way to infinity. So we have to be very careful when we look for the domain and range from the graph. When you see these arrows at the end, okay, that means you have all of your x values on that graph. You could possibly have some on the interior missing, but this is filled in and this is open, so we are okay. Range, what do we have? We can find the lowest point on the graph here and then go all the way to infinity, as you can see. So we will start at -10 and include -10, go all the way to infinity. Looking at the domain in number 19, as you can see again, all x values are covered, but look at this. This is a closed point. So our x values start here, we're covered here, keep going, but then we're closed here. So now you can see that our domain is -infinity to 4, and that's including 4. Taking a look at the range, the y values begin here and go all the way to this point. So what do you notice? We also have this gap here. So I didn't really draw that very good. So let me do that again. So we have this y value, and then we have a y value from here to here. So we actually have y equal to 1, and then we have y equal to 2 all the way to 8. So this is just a single y value there, okay? Okay, taking a look at our domain, we're starting here at -2, and this arrow means on and on and on forever. So this will continue on. So our domain will be -2 to infinity. Now, looking at the range here, we will go to our highest y value here, or we could start at the lowest. And as you can see, because of that arrow, we'll go from -infinity all the way to this y value, which is 1, 2, 3, 4. So that range will be from -infinity all the way to 4. Okay, and finally, let's talk about using the graph to answer questions. So what are they asking for here? This is asking when x is equal to -3, what is y? Here we're asking when x is 0, what is y? So let's answer those first. Let's go to our graph. And when x is -3, there's 1, 2, 3, there's the point on the graph. And that y value is a -3. Let's try that again over here. Maybe I'll raise this up just a bit, just so you can remember what those are asking. When x is 0, we have this value right here. And so when x is 0, it looks like y is 2. Okay, let's keep going. Find all values for x where y is -1. So we're looking for when y is -1, what is x? So let's go to y equal to -1. Here's y equal to -1. And I only see this one point. And that point is when y is -1, x is equal to -1. Okay, when y is -1. Okay, let's take a look here. This is saying when y is 1, what is x? So let's go back, and when y is 1, I only see one x value. It is open here, so that is not a point. So that would be x equal to 2. Now they've asked us to find the x-intercept. Remember, the x-intercept is where the graph crosses the x-axis. This is when we let y equal to 0. And there is none. There are no x-intercepts. Okay, how about the y-intercept? That's where the graph intersects the y-axis. That's when x is equal to 0. And what do you notice? We have that point right here, and that's y equal to 2. So it intersects at y equal to 2, and that point is 0, 2. Okay, let's take care of the domain and range, and then we will be finished. So looking at the domain here, if you can see this arrow here, -infinity, we're covered here at -1 all the way. So we do have -infinity to infinity. Every x value is there. We do have a gap right here for the range. So let's go ahead and draw the range on the outside here. So we have go all the way here, and then it stops, and then it's open, and then we go all the way. So what we have is closed here and open here, so we can close that. So the range will be -infinity, going all the way to -1. And then we'll start back up again at +1 and go all the way to infinity. And that concludes this section.